Welcome, everybody. We are extremely excited to be holding this event, honoring and celebrating the Turing Award winners. As you may be aware, their story is one of remarkable grit and perseverance. It's hard to imagine today, but neural networks were a profoundly unpopular research topic at the time that Jeff, Jan, and Joshua made many of their key contributions. And look at where we are today. Their contributions are at the heart of modern computer vision, natural language processing, speech recognition, and beyond. We see this reflected not only in the AAAi program, but also in our daily lives. We talk to our phones, we take pictures of text in foreign languages, and we instantly get the translation. Their story is an inspiration to follow your scientific heart rather than whatever is popular at the moment. Please join me in welcoming the Turing Award winners. And just the format of the event, each of them will give a 30-minute lecture. There will be no questions at that point. At the end, we have a panel, and then we'll take questions as well. Meanwhile, if you want to submit a question online, please see the instructions on the screen.
All right, it's my great honor to introduce Jeff Hinton. Jeff split his time as a professor of computer science at the University of Toronto and as a scientist at Google Research. Jeff is known for his fundamental contribution to AI and discovered backpropagation with his collaborators. He invented AlexNet, Boltzmann machine, capsule network, and many models and algorithms that we use today. So I was supposed to tell a small joke and a personal thing about Jeff, so hope this is not offending you. Jeff told me once, and possibly others, long time ago, that when he told his daughter that he discovered, he figured out how brain works, her reaction was, "Oh, Dad, not again." The funny thing is, I believe they have the same conversation every 5 years, or maybe become every 3 years, or maybe 50 years. I don't know. I'm wondering what Jeff is going to tell us today. Now, with a pleasure, welcome Jeff.
Okay, today I'm going to talk about some joint recent work with Adam Kosuriak, Sarah Sabor, and Yu Wei. And I'm not going to talk about philosophical things or why I stopped coming to AAAi or anything like that. I'm just going to talk about this work. So there's two approaches to object recognition. There's the good old-fashioned parts-based approach, where you have sensible modular representations, but it typically involves a lot of hand engineering. And so they typically don't have a deep hierarchy of parts that's all learned. And then there's convolutional neural nets. Convolutional neural nets learn everything end to end. They get a huge win by wiring in the fact that if a feature detector is good in one place, it's good somewhere else. That allows them to combine evidence and generalize nicely across position. But they're very different from human perception. And the first part of the talk is aimed entirely at Jan, and it's about the problems with CNNs and why they're rubbish. So CNNs are designed to cope with translations. They're not so good at dealing with other effects of changing viewpoint, such as rotation and scaling, although they're better than you might think. One obvious approach is to use 4D or 6D maps instead of 2D maps, but that just gets hopelessly expensive. So typically, CNNs are trained on many different viewpoints in order for them to generalize across viewpoint. And that's not very efficient. We'd like neural nets that generalize to new viewpoints effortlessly. If they've learned to recognize something, and you make it 10 times as big, and you rotate it 60 degrees, it shouldn't cause them any problem at all. We know computer graphics is like that, and we'd like to make neural nets more like that. So first, let me distinguish equivariance from invariance. The aim in convolutional nets, particularly when you do pooling, is to get representations that are invariant to changes in viewpoint. And that's different from getting representations that are equivariant. The idea of equivariant is, as the viewpoint changes, something about the representation changes. So my belief is that in our perceptual systems, when your viewpoint changes, the pattern of neural activity changes. Not the pattern that represents the label, obviously you want that to stay the same, but the pattern that represents your percept changes a lot, and that what doesn't change with viewpoint is something about the weights, and the weights are encoding relationships between things. That'll become clearer later. CNNs also don't parse images. When a CNN recognizes an image, if you just do it in one pass, it's not doing any kind of explicit parsing saying this belongs to that and this doesn't belong to that. Instead of that, CNNs, you can think of CNNs as you're centered on various pixel locations and you get richer and richer descriptions of what's happening in that pixel location that depends on more and more context. And in the end, you get such a rich description that you know what objects are in the image. But they don't explicitly parse images. CNNs clearly recognize objects in a very different way from people because I can take an image, add a tiny bit of noise, and CNNs will recognize it as something completely different, and I can hardly see that it's changed. And that seems really bizarre. And I take that as evidence CNNs are actually using very different information from us to recognize images. It's not that it's wrong, they're just doing it a very different way, and their very different way has some differences in how it generalizes. A further complaint about CNNs is they activate things by taking the scalar product of activities in the layer below times some weights. And that provides evidence, and they add up evidence. If they've got enough evidence, things turn on. There's a very different way to activate things, and that's by looking for coincidences. So coincidences are really important. Like most of physics is about coincidences between two different measurements you can make, the two sides of an equation. There's coincidence between theory and experiment. In high dimensions, if you get a high-dimensional coincidence, that's very significant. If you're filtering radio traffic and you see 9th of September, New York, and then in some other message you see 9th of September, New York, just a few of those, if they're all 9th of September and then New York, that's extremely significant because it's a higher dimensional coincidence. Now, the types of neurons we currently use don't do coincidence. That's no longer true because we started using transformers, and transformers do some coincidence, as I'll explain later. It's much better to activate things by the scalar product of two activity vectors. Do these activity vectors match? If so, get active. And that's what transformers do. And that makes for better filters. It also makes things that are better at responding to covariant structure. And in images, it's the covariant structure that matters, covariant structure of the pixels. And the final and worst problem with CNNs is they don't use coordinate frames. So whenever you see anything, you see a shape, you impose a coordinate frame. It's a fundamental aspect of human perception, and I'm going to try and convince you of that. Since I don't have much time, I'm going to try and convince you of it very quickly. I have some beautiful demos that would convince you, but I don't have time for them. The margin's not wide enough. So you'll see a country there, and the country looks a bit like Australia. As soon as I tell you that it's not vertical, it's tilted, you can see it as Africa. And once you've seen it as Africa, it just looks completely different from when you saw it as a kind of mirror-flipped Australia. But people don't initially see it as Africa. They see it as some country they don't know, if they're told it's a country. If you look at the example on the right, you can see that either as an upright diamond or as a tilted square. And your percept of it is utterly different depending on which way you see it. If you see it as an upright diamond, you're acutely aware of whether the left side corner and the right side corner are at exactly the same height. You'll notice a tiny difference in height. But you're actually not at all aware of whether the angles are right angles. You just don't notice it. So if I deform it by putting the two corners apart vertically, the angles won't be right angles, but it'll still look like a perfectly good diamond. If, however, you see it as a tilted square, you're acutely aware of whether the angles are right angles. If I change them by 2 degrees, you notice it. But you're not at all aware of whether the two corners on the sides are at the same height. So you've got a completely different internal percept depending on what coordinate frame you impose. And convolutional neural nets can't really explain that. You give them an input, they have one percept, and the percept doesn't depend on imposing coordinate frames. And I would like to think that's linked to adversarial examples and linked to the fact that convolutional nets are doing perception in a very different way from people. So I think a very good approach to computer vision is to think of it as inverse computer graphics. This is far from new. It goes all the way back to Bertolt Horn, I think. Actually, probably way before that. So graphics programs use hierarchical models in which they model spatial structure by matrices that relate the coordinate frame embedded in a whole to the coordinate frame embedded in a part. So you have to take a whole object, embed a coordinate frame. You have to choose what it is. For a part, you have to embed a coordinate frame. Once I've done that, I can say how the part relates to the whole. And that's just a matrix operation. We're going to take rigid objects for now. And that means it's a linear relationship. Okay? So there's this very simple linear structure, and that's what computer graphics uses. And that's why someone in computer graphics, if you say, could you show me that from another angle? They don't say, oh, well, I'd like to, but we didn't train from that angle, so we can't show it to you from another angle. We could show it for you rotated 15 degrees if that'd do, but that's about it. They just show it to you from another angle because they have a real 3D model, and they model a spatial structure as the relations between parts and wholes, and those relationships don't depend on viewpoint at all. Okay. I think it's crazy not to make use of that beautiful structure when dealing with images of 3D objects. One reason being that we know that the things you can generalize for long distances, the things you can really extrapolate are linear models. If it's higher order than linear, it's very hard to extrapolate well. But linear models you can extrapolate a long way. And we're always looking for linear underlying manifolds. And we know what they are with computer vision. Viewpoint is the thing that has most effect on an image. And there's a linear structure underlying that, and we're not making use of it. Okay, so now I'm going to talk about a particular system called stacked capsule autoencoders. And for people who've read anything about capsules, I want to try and make clear this is a different version of capsules. Every year, there's a completely new version of capsules. So there was a version in 2017 in NIPS that did routing. And then there's a version in 2018 in ICLR that used the EM algorithm. And there's this new version in Europe's in 2019, which is what I'm talking about now. So forget everything you knew about the previous versions. They were all wrong, but this one's right. So, previous versions used discriminative learning, which I knew was a bad idea. I always knew unsupervised learning was the right thing to do. So it was bad faith to do the previous models. They also use part-whole relationships, which is very dodgy. It's much better to use whole-part relationships. If you try and use part-whole relationships, if the part has less degrees of freedom than the whole, like if it's a dot and you're looking for constellations of stars, you can't predict the pose of a constellation from just knowing where one dot is. You need to use many of them. So an individual part can't make predictions for the whole. So in this new version, we're doing unsupervised learning, and we're using whole-part relationships. So the idea of a capsule is to build more structure into neural networks and hope that that extra structure helps you generalize better. And it's motivated by CNNs. In CNNs, Jan put in just a tiny bit more structure, very simple structure. Make your feature detectors be replicated across translation, and that's a huge win. And the question is, can we go a bit further like that? And can we perhaps also get in some more modular structure so we can get parse trees and things? So a capsule is going to represent, it's going to have something that represents whether it's there. It's going to learn what entity it should represent. And it's going to have some parameters of that entity. And in the 2019 version of capsules, which is the final and correct version, there's going to be a logistic unit, that's the pale blue thing, that represents whether or not this entity exists in the current image, in whatever location this capsule is covering. So capsules can themselves be convolutional. It's going to have a matrix, that's the thing in red, that represents the spatial relationship between the entity being represented by this capsule, or rather the embedded intrinsic coordinate frame of that entity, and the camera. So it tells you what way up it is and how big it is and where it is and so on. And it's going to have a vector of other properties, which will include things about deformation, and if you're dealing with video, they would include things about velocity and color and so on. And to repeat, because this is the important point, they're going to be good at capturing intrinsic geometry. So a capsule that represents an object can predict from its pose what the poses of the parts are, and the relationship between its pose and the pose of a part doesn't change when I change viewpoint. If I rotate the whole object, the relationship between the whole and the part stays the same. And so that's what you want to put into the weights of a neural network. That's the kind of knowledge you want to store, and then you want to do recognition using this knowledge that doesn't depend on viewpoint. So this is the slide you need to try and understand, and if you understand this slide, you understand the new model. The idea is we're going to have a kind of autoencoder. We're going to initially just do it greedily, where you take some pixels, from some pixels you derive some parts, from some parts you derive larger parts, from larger parts you derive larger parts. And it's going to be greedy because once you derive the parts from the pixels, you're not going to top-down revise your estimate about what the parts are. You're going to live with that, and you're going to, the next level up, try and find how to put these parts together to make a familiar whole. So what I'm showing you is the decoder for one two-layer autoencoder. But the units we're using are not neurons anymore. They're these more complicated things called capsules. So at the bottom level, we've got some capsules that we've already inferred from the image. So this is kind of the inductive step. We've already got some lower-level capsules. You know whether they... Ooh. You know that's quite aversive. You know whether they exist, what their vector of properties is, and what their pose is, how they're related to the camera. And having extracted those, you now want to learn the next layer, or you want to infer the next layer, which is some higher-level capsules, and preferably, you'd like one of these higher-level capsules to explain several of the lower-level capsules. That's when you know you're sort of making progress. You've explained several of the capsules you've seen, the part capsules, with one whole capsule. Okay, so in the generative model, we're not actually generating the lower-level data. We're generating predictions for what the lower-level data should be from the higher-level capsules. And the first thing we do is we take the vector of parameters in a capsule, and those dotted green lines say, using those parameters that we've extracted for this entity, we predict for a particular part what the spatial relationship of that part with the whole will be. If it's a rigid entity, you don't need the dotted green lines. The green matrices there can just be constants. But for flexible things, you need those dotted green lines. Then each higher-level capsule, I'll explain how they're instantiated later, but each instantiated higher-level capsule makes a prediction for the pose of each lower-level capsule that you've already extracted from the image. So in that kind of vertical ellipse with the three red boxes in, those are the predictions of three different high-level capsules for the pose of a particular lower-level capsule. And what we're interested in is that one of those guys should be capable of explaining it. So we use a mixture model. The underlying assumption of a mixture model is that one of these things is the explanation, but typically I don't know which. Now we have an objective function, which is we would like to maximize the log probability of the pose that we've already observed for the lower-level capsule under the mixture model produced by the higher-level capsules. So under that mixture model, you can compute the log probability. And the way we're going to train this whole thing is by backpropagating that up in order to learn what higher-level capsules to instantiate. And when you backpropagate through a mixture, what happens is elements of the mixture that were no good at explaining the data have basically zero posterior responsibility, and when you backpropagate, there's no point in fixing them up because they're not helping. The element that does the best explanation typically gets the biggest derivative, and you fix that up. Okay, so I'm going to run out of time if I'm not careful, but this is the generative model, and notice the generative model has two things built into it. It's got the idea that each lower-level capsule is explained by exactly one higher-level capsule. That's the idea of a parse tree, right? In a parse tree, things have one ancestor. It's also got the idea that the pose of the lower-level capsule is derived from the pose of the higher-level capsule by doing a matrix multiply between the relation of the high-level capsule to the camera and the relation of the part to the whole, and that will give you the relation of the part to the camera. So we built in the sort of two of the most important things in vision, which is dealing with viewpoint and deriving paths trees. But what I haven't done is shown you how to do the encoder here. And of course, that's what perception is. Perception is the encoder. So we've got a tough inference problem. We tried in previous versions of capsules engineering the encoder by making votes for the poses of higher level capsules and seeing if the votes agreed. And that was really finicky. It was really hard to get it right. Sarah Sabor put a lot of effort in and she did make it work, but it was difficult. Fortunately, while we were doing this, transformers came along. They were used for language, and transformers were really neat. And what we're going to do is simply say, we've got this nasty inference problem. You've got some parts. You want to infer the wholes. Why don't I just give all of the parts to a transformer and tell it to get on with it? And let's make it a multi-layer transformer. So we're going to have a simple generative model, but a complicated encoding model. This multi-layer transformer, it's going to decide how to organize agreements and things. All you need is to be able to train it. And to train it, you need to get what the right answer is. Well, actually, you don't need the right answer. All you need to train it is derivatives. You need to see what answer it gives and tell it how to give a slightly better answer. And that's what you get from the generative model. So we take all of the already extracted capsules, we feed them into the multi-level set transformer. The set transformer basically takes a vector description of each of the lower-level capsules and keeps revising that vector description as you go up through the set transformer, using the context of the descriptions of other capsules that you've got. And once these descriptions of parts have been revised enough, then you have a final layer that converts them into predictions for what the whole object should be. So the set transformer is easy to train because we've got a generative model. The generative model gives us the derivatives for the set transformer. It's got the same objective of training the generative model, which is simply to maximize the log probability of the observed poses of the parts given the existences and poses of the higher level capsules. We also throw in a sparseness prior to encourage it to only activate a few high level capsules. So this is the reference to the paper on set transformers. I'm not going to go into great detail about how they work. I imagine many of you know how transformers work, and I don't have much time, so I'm going to go very, very fast through how transformers work. This is for sentences, right? The way to process a sentence is to get a sequence of word vectors and apply a convolutional neural network so that each word vector gets revised based on its neighbors, and then you could train the whole thing unsupervised to be able to reconstruct the word vectors if you left a few out. That would be a convolutional way to do an autoencoder, a deep autoencoder. Transformers are basically like that with a little more elaboration. So instead of a word vec directly influencing the word vec above, and instead of these direct influences between the word vecs at one level and the word vecs at the next level, every word vec will generate a query, a key, and a value. And from the point of view of the word vec that this slide is focused on, it looks at its query, which is a vector that's been learned, and it compares its query with the keys that neighboring word vecs are producing. And if it finds a good match, it says, send some of the value produced by that neighboring word vec to be my new value. So it's really attending to things that are similar and combining them to get a new representation. That's how transformers work. So now I'm going to show you what we can do by using a set transformer and a simple generative model that's got built-in coordinate transforms and parsing, and what it'll do on some relatively simple data. So you mustn't laugh. These are MNIST digits. These are things from the 1980s. It was the 1980s, right? Yeah. These are difficult examples of MNIST digits, sort of marginal cases. And that's what I'm going to apply this to. So this is just sort of making sure the idea works. So the way we're going to model MNIST digits is we're going to have a layer of parts, which are going to be little bits of stroke, and we're going to have a layer of holes, which are going to be things like whole digits, so higher level capsules. They're not exactly going to correspond to digits. So the parts are little 11 by 11 templates that get learned. I'm not going to go into much detail about how the parts are learned. It's basically the same way as the holes are learned, so I'll focus on how the holes are learned. You're essentially modeling each pixel intensity by a mixture model of predictions coming from the various parts. And each part can be affine transformed, that is, it has this pose matrix that allows it to instantiate itself differently. So if I show you some digits, then if you look at that 4, what I'm going to show you in red is what happens if you extract from the image the parts of the 4, and then from those parts, you reconstruct the 4. And what I'm going to show you in green is what happens if you extract from the image the parts of the 4, and then from those parts of the 4, you activate the higher level capsules, and then from those higher level capsule activations, you reconstruct lower level capsules. You actually generate them from the higher level now. And then from those lower level parts, you reconstruct the pixels. And I'm showing you that in green. And if the red and green are exactly the same, you'll see yellow. And you see yellow with red and green fringes where they differ just slightly. What I'm showing on the right is the activation of the 24 high-level capsules. So these 24 high-level capsules are going to learn to be things like whole digits, but they're going to learn to be much larger things, but not exactly digits. Just to show you how it makes up things out of parts. If you look at the 4, and you look at the column for part 5. Part 5 is the same part, but with different affine transformations. And you can see that as I change the affine transformation, it gets instantiated very differently in the image. And so the same part can be used in very different ways. But it can make these digits out of these affine transformed parts. Now what I want to show you is, after we've learned, so we learn to extract parts, then we learn the holes to explain these combinations of parts. And then we take these high-level vectors, so those things that occur in those activation patterns of that block of 24 high-level capsules, the things in the right column, and we take those vectors of activations and we plot them with t-SNE. That is, we embed the vectors in a two-dimensional map such that similar vectors are close to one another and dissimilar vectors are far away, but with the emphasis being for similar ones to be close. And what we get when we embed those vectors in a map, and remember, this is something that's never seen a label in its life. It hasn't been told anything about labels. It's purely unsupervised, is we see that. So it's got 10 classes, and the 10 classes are well separated, and it's got some mistakes. But if you now simply say, I'll give a label to each class, so I could, for example, pick one member of each class and see what its label was, and almost certainly it would have the right label, the label of all the other things in the class. I can then do 98.7% correct on MNIST with basically no labels or with 10 labels, depending on how you look at it. So the natural classes of MNIST pop out from learning with a generative model that's got this wired-in idea of parts have particular coordinate relations with the whole. And for MNIST, they're deformable things, so it needs those dotted green lines I had to say the relation between the part and the whole is a function of the particular whole you've got. So it works. And I have 3 minutes left and 3 slides left, so that's perfect. There's 2 big problems with this. One problem is that vision is not really taking a whole image and processing it. Vision is having a tiny fovea and deciding where to put it. So the outer loop of vision is a sampling process, and we don't see almost everything at high resolution. When we're doing vision, on each fixation, I firmly believe that we see one figure and some ground. And of course, there's all these illusions where you can see a vase or you can see two faces. A pair of faces, which is one thing. Or you can see one face, which is a different thing. So if vision psychologically consists of a figure with ground, this capsule model is a model of the perception of the figure. It's not meant to be a model of the perception of the ground. To model the ground, you need something that does something far more like texture modeling and doesn't carve things up into parts. And a variation autoencoder is very good at that. So Sarah trained a combination of a stack capsule autoencoder and a variational autoencoder to explain MNIST digits with highly textured backgrounds. And it turns out that works much better, and the variational autoencoder models the background. It still doesn't work as well as not having chunky background, but I believe the way to make this kind of theory work with background clutter is just to the same way as people, and to say the background clutter, we just treat it as background clutter. We don't model it with a high-level part space model. That's reserved for the figure. Okay. And the next point, sorry, I already said that. The next point is, this was all 2D, and we need to deal with real 3D images. Sarah made a previous version of capsules work on the Norb images, which were designed by Jan to test out whether things can deal with 3D shape, real 3D shape without using color histograms. To make this stuff work, we need the front-end capsules, the primary capsules, to represent sensible parts of objects. And if you think about vision as inverse graphics, graphics takes whole shapes, gets parts of parts and parts of parts, and eventually gets down to something like triangles, and then it renders them. And so if you want to do inverse graphics, the bottom level is going to be inverse rendering. And it's only the bottom level that deals with the properties of light and things like albedo. Higher levels are going to be to do with geometry. And what I've been talking about is the levels to do with geometry. So we're working now on inverting renderers so you can get sensible parts. And we've got a number of different ways of doing that. You can use surface meshes, or you can use known parts, which are sometimes called geons, or you can use intersections of half spaces. And there's a whole bunch of different approaches. And I have 6 seconds left, so I better have a conclusion. Prior knowledge about coordinate transforms and parse trees is easy to put into a generative model. One interesting thing about putting your knowledge into a generative model is the recognition model, the encoder, does not enter into the complexity of your model. You can make the encoder as complicated as you like, and in minimum description length terms, or in Bayesian terms, it's the generative model's complexity that counts. So make a simple generative model that has lots of wired-in structure, and dump the awful problem of inverting it onto a great big set transformer. And if you make the set transformer big enough and with enough layers and you train it on enough data, success is guaranteed. Okay.
So it's my pleasure to introduce Jan LeCun while he's setting up his topic. So Jan is the chief AI scientist at Facebook, and also he was the first director of the New York Facebook AI Research Lab that he then expanded to many other locations in France, in Canada, and the US. And he's also a professor of computer science, data science, neural science, and electrical and computer engineering at NYU. He has been working, as you know, in the field of machine learning, but also computer vision, mobile robotics, and computational neuroscience. Personally, I met Ian a few years ago at an NYU meeting that he organized on AI for Good, where the idea of the partnership on AI came about. And from then, we worked together with other people as well. And it was great working with him to see, how this passion of making AI really advanced but also beneficial came together into this great initiative. But besides his amazing technical and leadership role, it always struck me about Ian the fact that he's really a very positive person. You can see that he really enjoys the research that he does. He's always smiling when he talks about his research. And he really loves life. He's a great, likes sailing a lot. He likes good food, especially French food. And since I'm the Italian one among the 3 chairs, I was assigned to say this sentence, which I think we need to say here, because together with Jeff and Joshua, Ian is one of the so-called godfathers of AI. So please join me in welcoming Ian LeCun.
Well, there's something else I have in common with Italian godfathers, which is that I have a house in New Jersey. Okay, I'm going to talk about self-supervised learning. This is going to be a higher level talk than what Jeff did, more sort of inspirational than technical, really. And I need 2 microphones. Okay, first I'll start with a definition of deep learning because I'm pretty active on various social networks, and there seems to be a confusion about really what this is. And it's not supervised learning, it's not neural nets, or it's not just neural nets. It's basically the idea of building a system by assembling parameterized modules into computation graph. Those graphs can possibly be dynamic in the sense that they're not determined necessarily, they're not static. They can be, they can depend on the data, on the input data, on a case-by-case basis. And then you optimize those using gradient-based learning. That's a very, very general definition, but it's the idea that you don't directly program a system. You kind of write a program that defines an architecture, but there is some parameters left, and you adjust those parameters through learning. There can be billions of those parameters. And we've seen the example that Jeff described earlier is basically a good example of how you engineer architecture. So it gives you a language for engineering prior knowledge into a system, or inductive bias, as machine learning people like to say. So one thing that also deep learning can go a little beyond the sort of common idea of neural net is the idea that the output is not just necessarily computed by some feed-forward process that just goes through those modules, but it could be the result of some complex computation that, for example, consists in minimizing some energy function of some kind, right? So you can have inference in deep learning systems. And then it doesn't specify the learning paradigm. So of course you can use deep learning in the context of supervised learning, which is very successful, but also in the context of reinforcement learning, that's also been very successful, at least for games, and as well as in the context of self-supervised or unsupervised learning. So we read a lot about the limitations of deep learning today, but most of those limitations are actually limitations of supervised learning, not limitations of deep learning. Okay, with that out of the way, supervised learning really works. But it works really well, but it requires a lot of samples. In fact, probably one of the reasons why neural nets kind of died in the mid-90s is because the few problems for which we could have enough data at our disposal was very, very restricted. It's basically handwriting recognition, a little bit of speech recognition, but that was about it. And so we couldn't really train large networks, partly because we didn't have the data, partly because our machines were too slow, partly because there were some concepts that we hadn't figured out yet. But that's kind of what changed over the last 10 years or so. So it works really well for speech recognition, image recognition, as you know, NLP in general, translation, things like that. I think the progress has been really stunning in computer vision, and in fact caused an explosion of the field in applications of computer vision. And the nice thing is that a lot of this is all available in open source. You can download various pieces of code from various places and basically be sort of high performing in terms of any computer vision problem you want to solve. And all of this runs in real time and everything. So this is stuff we expected from deep learning, but there's also stuff we didn't expect from deep learning. Or at least I didn't expect. This is some very recent work over the last few months by some of my colleagues at Facebook AI Research in Paris, Guillaume Lample and François Charton, and they showed that you can do symbolic manipulation with deep learning. You can do things like solve integrals symbolically. And the kind of architecture they use is a transformer, which I don't have to describe because Jeff just did this partially. So they use a fairly large transformer, and they train it in supervised mode by kind of generating equations in a somewhat sophisticated way, and then presenting the integral of, not an equation, but a formula, and then training the system to produce the integral of that formula symbolically. They've done this also for first and second order differential equations. And this system works really well on the data set that they generated, and they've shown that it solves a lot of problems that both MATLAB, Maple, and Mathematica cannot solve. So that's really impressive. It's pure supervised learning with generated data with a very large neural net, and it seems to be doing some sort of symbol manipulation without actually doing symbol manipulation, because everything in that system is represented by vectors. And so there's no symbol, there's no logic, there's no rules. It's basically a large neural net that is trained to do this. And so it's kind of the intuitive form of symbolic integration, if you want, or integration of functions or differential equations. Second thing is, deep learning is pervasive today in the short amount of years that it's appeared. And I was given a statistics that I found stunning. Automatic emergency braking systems are now standard in a lot of cars. In Europe, actually, they're standard in every car, including very low end. So those are basically a convolutional net plugged into a camera, that looks out the windshield, and decides to activate the brake if they detect an obstacle in front of the car, and the driver somehow is inattentive. According to the statistics, this reduces collisions by 40%, and so it saves lives. We read a lot about the negative effects of AI, but that's a positive effect. There's, of course, a lot of excitement about the use of deep learning in the context of medical imaging for mammograms. These are pictures from work from my colleagues at NYU. But there is also a lot of use of AI that is a little behind the scene, that despite what you can read in a lot of the media and the press, things like hate speech, filtering, call to violence, stopping weapon sales and things like this, and terrorist propaganda on social networks of various kinds in companies that employ some of us is really useful. There's a lot of that going on the web, and a lot of it has to be taken down, and this is done with deep learning. You take out deep learning from Facebook, Instagram, Google, YouTube, etc., and those companies crumble. They are completely built around it now. The things that are more visible, like translation, of course, but that's interesting. So there's been, of course, a lot of excitement about reinforcement learning, and it works really great for games and simulation, but it's very slow in the sense that it requires many, many, many trials to train a system to kind of reach any kind of performance. So, for example, a Go player that was built at Facebook, somewhat similar to AlphaZero from DeepMind, takes roughly 2 weeks to train on 2,000 GPUs, and it has to play 20 million games, which is more than any person can play in a single lifetime. The StarCraft playing system AlphaStar from DeepMind took the equivalent of 200 years of real-time play to reach slightly above human performance on a single map. And the recent OpenAI single-handed Rubik cube manipulation system took about 10,000 years equivalent, in simulation. So those systems, work really well in simulation, but what about the real world? So what if you want to train a car to drive itself? And, it's very hard to kind of simulate this really accurately. And so we can't really do it in the real world because we will have to, destroy many cars doing so, and then run the car millions of times, etc. And so it's a big challenge, which is how do we get machines to learn a little more like humans and animals? How is it that humans can learn to drive a car in 20 hours of training without crashing for most of us? So that's one of the challenges of deep learning. I see 3 challenges, and these are things that all of us are working on to some extent. As I said, deep learning works well for perception. Deep reinforcement learning works well for action generation, only when trials are cheap. So it only works in simulation mostly. But there are 3 problems that the community is working on and should be working more on. The first one is, how do we learn with fewer labels, fewer samples, or fewer trials? And my suggestion on it, which I stole from Jeff, basically, after ignoring him for 15 years and then changing my mind, is to use unsupervised learning, or I prefer to call it self-supervised learning because the algorithms we use are really akin to supervised learning, which is basically learning to fill in the blanks. And transformers and things like that are an example of this that I'll come back to. So basically, it's the idea of learning to represent the world before learning a task. And this is what babies do. And animals also do this, right? So we learn about the world, we learn how it works before we learn any task. And once we have good representations of the world, learning a task requires few trials and few samples. The second challenge is learning to reason. So I just showed an example of how you can do symbol manipulation without actually doing symbol manipulation. And the question is, how do we go beyond sort of feed-forward computation that Danny Kahneman, who is sitting right here, calls System 1. I'm not going to talk too much about this because I know Joshua is going to talk about that. But sort of the question is, how do we make reasoning compatible with basically gradient-based learning? Okay, how do we make reasoning differentiable? That's kind of the bottom line. And nobody has really kind of complete good answer to this. It's a challenge. And then the third one is, how do we learn to plan complex action sequences, decompose a complex task into subtasks? And we can, with convolutional nets and capsules and stuff like that, we can learn hierarchical representations of images, speech, text, etc. But how do we learn hierarchical representations of action plans? We have no idea how to do this. So I'm going to talk a little bit about number 1. Number 2, I alluded to, but I'm not going to come back to this too much. And number 3, I have no idea how to solve it, so I'm not going to talk about it at all. But I'm open to any idea you may have. So how is it that humans learn so quickly and so efficiently? And it's not supervised, it's not reinforced, right? So I stole this slide from Emmanuel Dupoux, who is a cognitive scientist in Paris and spent some time at Facebook. And if you show the scenario at the top left to a baby, where a little car is on a platform and you push the little car off the platform and the car doesn't fall, there's a trick. A 6-month-old baby will look at this like, like nothing, right? Doesn't seem very interesting to that baby. It will look at it like it look at everything else. If you show this to a 9 or 10-month-old baby, she will look like the little girl in the bottom left. Because in the meantime, around 8-9 months, babies learn about gravity. So they learn that objects that are not supported are supposed to fall. So when an object sort of violates that rule, they get extremely surprised. And they look at it like crazy because they figured they missed something. So that's a way of trying to figure out if babies have learned basic concepts. And there is this idea that going back to Piaget and earlier, that babies learn concepts kind of one after the other in sort of more and more abstract and more complicated concepts one after the other. So babies learn pretty early about object permanence. Some people claim it's actually hardwired. That's a big question. They learn to distinguish animate objects from inanimate objects fairly early in the 3 months or so. They learn categories pretty quickly as well, without being told the name of anything. And they learn about gravity, inertia, and conservation of momentums, and things like this, intuitive physics around 9 months. How do we do this? And it's not just babies, it's animals. Here is a baby orangutan here. He's being shown a magic trick that has to do with object permanence. You put an object in a cup, shake the cup, remove the object, but the orangutan doesn't see that. The cup is now empty. Show the empty cup. And the baby orangutan rolls on the floor laughing. because his model of the world was violated. He knows about object permanence. Orangutan, by the way, don't have language. They're not even social animals. They live solitary lives. So, that tells you something about how you can be intelligent, not necessarily with language or sort of linguistic communication. Okay, so what is self-supervised learning? Self-supervised learning is what made the success of NLP over the last year and a half or so. It's the idea that you train a system to fill in the blanks, right? So you show a system a piece of input, a text, a video, even an image. You suppress a piece of it. You sort of mask it if you want. And you train a neural net or your favorite class of model to predict the piece that's missing. So it could be predicting the future in a video, or it could be predicting missing words in the text. Predicting missing words in the text is exactly what transformers and BERT-like systems, of which there are many followers now, are built to do. You show a segment of text to a giant neural net. The biggest ones have billions of parameters. You mask 15% of the words or so, and then you train this network to predict the words that are missing. And it's easy to train a system like this because there is some uncertainty about which word, of course, could be missing, but we can represent this uncertainty with a giant vector of probabilities over the entire dictionary, and so not a problem. But it's more of a problem for images, and the success of transformers and BERT have not been translated in the domain of images because it turns out to be much more difficult to represent uncertainty in prediction in images or in video than it is in text, because it's not discrete. We can produce distributions over all the words in the dictionary. We don't know how to represent distributions over all possible video frames. And so that actually, I apologize for the background, that actually creates a problem, which is that the world is not entirely predictable. There are many possible continuations to an initial video segment. And if you train a system to make a single prediction, train a neural net to predict the next few frames in a video, what you get are blurry predictions. The reason is that the system cannot actually predict what's going to happen in the future, and so it predicts the average of all the possible futures, and that happens to be a blurry image. So how do we solve that problem? So in my opinion, this is the main technical problem we have to solve if you want to apply self-supervised learning to a wide variety of modalities like video and things like that. So there's a number of different options, but my money is on this idea of latent variable energy-based models. So an energy-based model is kind of like a probabilistic model, except you don't normalize. You don't take exponentials and you don't normalize. So think of the energy as the negative log probability if you are a probabilist or a Bayesian. Other than that, it's just like a probabilistic model. Okay, so you have an energy function, in this case C of y bar, which measures the compatibility between an observation x and a prediction, a desired prediction y, which is also an observation. Okay, so x would be the initial segment of a video, y would be the future of that video. And then this energy-based system gives you the compatibility between those two. Now, there are several different futures that are possible. So what you have is a latent variable, z, in this diagram, that you can vary, and when you vary this latent variable, the prediction, y bar, varies over some sort of manifold, which is the manifold of plausible predictions, plausible futures. And there's a lot of work on this, not a huge amount of success yet, but some attempts using various ways of training those systems, adversarial methods or others, that seem to be kind of reducing this kind of blurriness. I'll come back to this in a couple of minutes. Okay, so this is an argument that Jeff has been making for decades, and as I said, I was skeptical for a long time, but changed my mind. And it's the idea that there is a lot more information you get, or you give a machine where you use this type of self-supervised learning or a form of unsupervised learning than there is if you train a machine to do supervised learning or reinforcement learning. So in reinforcement learning, you give the machine a feedback which consists in a single scalar once in a while. Okay, so inevitably, it's a very small amount of information that you ask the machine to predict. And so inevitably, it takes many, many, many trials for the machine to learn anything. In supervised learning, you give a few bits of information at at every sample, which is a category among 1,000 or something like this. And again, it's fairly weak, which is why you need so many samples. In self-supervised learning, you ask the machine to predict an entire video frame or even an entire video. And so it's a lot more information. And to learn the same amount of knowledge about the world, you might require fewer samples. The problem is that that data is unreliable because you need to deal with uncertainty. There are many possible futures. So that's the technical problem we need to solve if you want to scale self-supervised learning to kind of real-world applications. And that led me to this obnoxious analogy that if intelligence is a cake, self-supervised learning is the bulk of the cake, the génoise, and supervised learning is the icing on the cake, and reinforcement learning is the cherry on the cake. With my apologies for all the reinforcement learning people in the audience. Some of my best friends are reinforcement learning people, okay? This is not to say, this is, by the way, a forêt noire where, Black Forest cake, the cherry is not optional here. Okay, so the next revolution in AI will not be supervised, nor purely reinforced. You can even buy a T-shirt, apparently. Someone made a T-shirt out of this slogan. I stole the slogan from Alyosha Air Force. This is not mine. And he stole it from Jill Scott Heron. Okay, so I talked about this idea of energy-based models, and I don't have time to go into any sort of technical description of what this is, and I'm going to flash a very complex slide that I'm not going to explain, which is sort of various ways you can train those energy-based models. And there's basically two main categories of methods for training them. The first one that we call contrastive, and there's a lot of methods that you can read here that may relate to things you know. And the second one are architectural, and they are the ones that have my preference, but I'll start with contrastive ones. So one way to train an energy-based model is to train it to give low energy to samples that you observe and high energy to samples you do not observe. Back in the old days, Boltzmann machines are restricted. Boltzmann machines were trained with contrastive divergence, and that's an example of a contrastive learning method where you give a data point to a machine, and then you give it a non-data point, and then you push down the energy of the data point, push up the energy of the non-data point. So this is the energy computed by the model, right? So your model computes an energy function in output space, and you shape it in the appropriate way. Now, BERT-type systems, transformers, are pre-trained with a contrastive method, which is a special case of what's called denoising autoencoder, which came out of Yosha's lab by Pascal Vincent. And the idea of this is you take a sample, you corrupt it in some way, remove words in the sentence, for example, in the case of BERT, and then you run it through a network, and you train this network to recover the uncorrupted version of the data from the corrupted version. And with a little bit of thinking, you quickly realize that this is a form of energy-based training where you force the energy of the corrupted point to be higher than the energy of the uncorrupted point. So for some definition of the energy, which is kind of the reconstruction error, if you want. So that's one form that's extremely successful. Works really well for text. As I said, not so well for images. Here's another example that's more successful for images. Another example of contrastive training, and it's contrastive embedding. There's a number of papers on this that in the last couple months have brought about record-breaking performance on computer vision tasks using this method as kind of a pre-training phase and then sort of fine-tuning for a particular supervised task. There's one missing reference here, a more recent one from paper from Olivier Naff and his collaborators from DeepMind. But there are those three papers here are from Facebook. So DeepFace is kind of an old paper about face recognition, which is a bit of a specialized application. The two recent ones are so-called PEARL, which means pretext invariant representation learning by Misra et al. And second one, MoCo by Kaiming He et al. Both are at Facebook. And the idea there is it's kind of a mixture of various things, but it's based on the idea of Siamese networks, which I proposed many years ago. So you take an image, you corrupt it, but you don't corrupt it too much. And you show those two images to two neural nets, and you tell those two neural nets you should output similar outputs because the two things I showed to you are semantically identical, essentially. And then you take two different samples, so two different samples from your training data, and you show them through this, two parallel identical neural nets, and then you tell the system whatever output you produce should be different for those two samples. Now, the trick there, and the trick for both Perl and Moco, is how you pick those negative samples. So they have particular methods for doing what's called hard negative mining, and sort of choosing those samples so that they actually help for the training. But in the end, those systems work really well and sort of beat records in some standard data set. So that's at least one success in so contrastive self-supervised learning applied to image recognition. Okay. So what happens when you have an energy-based model with a latent variable is that if I give you an x and a y, what you have to do is find the value of the latent variable here that minimizes the overall energy output by the system. And you can think of this as a form of inference. Okay, so this would be an example of a neural net or a deep learning system where inference takes place, right? The way you compute the outputs and the way you sort of do inference in the system is you minimize some energy function with respect to the latent variable, and supposedly when you do inference with respect to the output variable as well. Okay, and so this could be sort of a general framework for kind of going to the next step, going from system 1 to system 2 by going from feed-forward to sort of optimization. Of course, the idea of doing energy minimization for inference is very, very far from being new. This is what's used in pretty much every probabilistic model, and structured prediction learning, which has a long history, also used this idea. So anyone who's used an HMM has used basically energy minimization for inference, for example. Okay, I'll end with a very simple example of how you can do prediction in a stochastic environment in a way to learn a world model. So learning something about the world by observation, and then so you're using what you've learned by observation to kind of learn a task subsequently. So the idea here is we want to drive a car around, and the problem with driving a car is that it's a good idea for driving a car to predict what cars around you are going to do. So what we do here is we train a forward model, and this forward model is going to predict what the cars around you are going to do. You're driving on a highway, and you're going to have the system that predicts what the cars around you are going to do. Perhaps you're going to run it for a few seconds, and that's going to allow you to plan ahead a sort of defensive policy to not crash into the other cars. Now, of course, there are many things that can happen to the cars around you, and you cannot make a single prediction. So that prediction will depend on a latent variable that we can draw from a distribution. And we also depend on the action you take. So the forward model here is going to take the current state of the world, where the cars around you are, your action, accelerating, braking, turning the wheel, some random latent variable, and it's going to spit out the state of the world 100 milliseconds from now. Okay, and then you can run this, you can roll this out. Now, we can compute a cost of a particular situation with the cars around you. If you are too close to another car, there's a high cost. If you are not in the middle of a lane, there's going to be a high cost for this. So we're going to just compute a cost that's going to tell us how good our position is. And that cost is going to be differentiable. So I am not talking about reinforcement learning here. This is closer to optimal control than reinforcement learning, in the sense that we don't need to estimate gradients or anything or whatever. We just need to optimize some criterion over a trajectory. What we're going to do, though, is we're going to use backprop to time for a particular scenario. We're going to start from a real-world situation, run our model forward for a few seconds. Okay, it's going to be imagine future, and then backpropagate gradient through the system to either find a sequence of actions that minimize the overall cost, or backpropagate those gradients all the way through a policy network that's going to compute the action that will sort of minimize the probability of accidents, if you want. So that's kind of what goes on. The training of the forward model is done by collecting data of an overhead camera that looks at a highway, and then extracting sort of little rectangles around each car, tracking every car, and extracting little rectangle around each car, which is the environment of each car. And then training a neural net with a latent variable from a few frames of the environment of that car, where the car is the blue car in the center, predict the next few frames on the next frame, and with the help of a latent variable. So I don't have time to describe exactly how this takes place and what the role the latent variable plays, but it's a combination of, for those of you who are familiar with variational autoencoders, it's kind of similar to this with some twist. So this is the kind of prediction you get. The column on the left is observed. The second column is if you have a deterministic predictor with no latent variable, and you get kind of blurry predictions. And then the 4 other columns are different predictions for different samplings of the latent variable, and what you get are different futures indicated by the cars that are tracked. So there's various tricks that have to be used for this to work, which I'm not going to go into, but after you train the system, you get a reactive policy that can actually drive a car in traffic without crashing too much. But you have to realize that this is an invisible car because it's being placed in a recorded environment. So all the green cars are recorded, and the blue car is invisible to them. So sometimes it requires that blue car to escape. So here the yellow car is what was actually observed, and the blue car that you can barely see is the one that's being driven by our agent, and it's invisible. And so now it gets squeezed, and it has to basically escape in between 2 other cars. Okay. Conclusion in the 0 second I have left. If my slide wants to switch. Okay, here we go. So I think self-supervised learning is the future, really. This is what's going to allow our AI systems or deep learning systems to kind of go to the next level, perhaps learn enough background knowledge about the world by observation so that some sort of common sense may emerge. I'm being a little provocative here. Because there is plenty of data, because it doesn't need to be labeled, we can train massive networks, and BERT and its followers are kind of an example of that. We could use those techniques to learn forward models of the world for control. And the challenge, of course, is handling uncertainty there. So reasoning through vector representation and energy minimization, I gave some, a couple examples, but there's a lot of work to do there. And then, as I said before, we need to replace symbols by vectors and logic by continuous functions. So basically, continuize discrete things, basically, to make it compatible with gradient-based learning. And then the last thing, the last challenge, learning hierarchical representations of action plans. I really have no idea how to solve this. So thank you very much.
So I'm going to introduce Yoshua Bengio. Now, to save some time, I'm not going to spend too much time on all his contributions so far. Higher dimensional word embeddings, attention mechanisms, generative adversarial networks. Most of you have heard a lot about all these things and all the impact that it has had. What I do want to talk a little bit about is that Yoshua is not at all content to just sit on his laurels. He continues to work very hard to tackle some of the greatest challenges in science, such as the nature of consciousness. He works extremely hard to make Montreal one of the great AI hubs on the planet, and with some success. And speaking of the planet, he is devoted to saving it from environmental disaster, and he has some very interesting ideas on remote attendance in conferences to make sure that we reduce the carbon footprint of our conference. And after this conference, I'll be particularly interested in his ideas on that. So please join me in welcoming Yoshua.
Thank you so much. So just like Jeff and Jans, my talk will be looking somewhat forward at how we can expand the amazing success that deep learning has had in the last few years. And I'll be taking up the point that Jan mentioned of reasoning and more generally what Dan Kahneman has called System 2 processing. So, first of all, I want to say a few general words about why we need to think about inductive biases. You know, theory that from the 90s, the no-free-lunch theorem tells us that there's no general, completely general machine learning. So there's no completely general AI, and so we need to consider priors. But then the question is, you know, how much prior knowledge should we put in? And of course, evolution has put a lot of very specific priors in all kinds of animals. But my belief is that the kinds of priors that evolution has enabled in human brains, some of them are really, really very general and allow us to tackle a wide variety of tasks. And in addition, because they are very general, they don't require many bits to be specified, which means that evolution probably can discover them more easily. So deep learning already incorporates many of these priors, and there are many priors. You know, ConvNets is a well-cited examples that exploit the invariance to translations and other kinds of deformations in images. But I'm particularly interested, and I have been for a couple of decades, in priors that have kind of combinatorial or exponential advantage. And I wrote a few papers a few years ago on the compositional advantages that already exist in current deep learning due to the combinations of features at each layer and the composition of layers. And today I'm going to tell you about another kind of compositional advantage, which I think we find in conscious processing and in reasoning. So if this, I want to mention this book, Thinking Fast and Slow, which has been a great inspiration for me, and talks about these two systems, System 1 and System 2, as two kinds of computations that the brain is doing. It's not that we have different parts of the brain that do that. Clearly, we don't know the answer to this, but they're really different at the behavior level, two different kinds of computations. So System 1, essentially, I would label as just intuitive or unconscious, and can be done without the presence of language. And in fact, we can't describe with language what we're doing at that level. And current deep learning is very good at these things. So that's one way to think about System 1. Current deep reinforcement learning is very good at these things. So habitual behaviors that need a lot of practice. Now, System 2 processing allows us to do things that involve consciousness, things that usually take more time to compute, things that usually are sequential, and where at each step of the computation we only examine a few elements. This is a very particular property of consciousness. And it's also a property of the way we humans reason, not necessarily machines as we program them. And my talk is going to be about how deep learning could do more of these things. The reason why I find this interesting to ask that question is because there's something about the way we do these System 2 tasks which is combinatorial, because what we do is we take things we know and we are able to recombine them in novel ways dynamically. So I have these pictures in the bottom where on the left, System 1, you're driving a known path and you can talk to someone else at the same time. You don't need to put your conscious attention on the driving. You should, but on the right-hand side, you're driving in a new place and maybe something strange is happening. You don't want to be bothered by somebody talking to you. You need your full attention on the task, and you're able to innovate, like, you know, plan a new path because there's some construction or something, right? So this kind of ability is the thing I want to focus on. And what's particularly interesting about this kind of ability, and I'm going to focus on that as the motivation for this, besides the inspiration from humans, is that it allows us, like in the example of driving, to deal with very novel situations that are far from what we've seen in our training experience. So, so that's what I call out-of-distribution generalization or out-of-distribution transfer, where there's some adaptation going on. So that's one of the motivations. And of course, the other one is the inspiration, trying to perform the kind of tasks that we also associate with language and learn high-level representations that capture these kinds of high-level representations that describe components, concepts that can be recombined on the fly. And many of these concepts also have to do with how we influence the world. And in other words, causality, which is another theme that I'll be talking about very much today. And then there's a third perspective to this. All of these things are just different views on the same problem. The need for generalizing out of distribution is something that's particularly important for agents in an environment, because the world changes and these agents need to understand how that world works so that when things change because of interventions of other agents or something, they can deal with that efficiently. And then there's another aspect that I won't talk about today, which is how the understanding we have of the world model we're building also helps us figure out a good strategy for exploring the world, for seeking new knowledge in an intentional way, which is what Baby do very, very much. So these three things are not independent. I'm trying to convince you that these are just different aspects of the same topic. So, so I want to go back to the notion of priors, right? So one of the things I find really exciting when I read a machine learning paper is when the authors are able to cast, say, a new algorithm in terms of an inductive bias or a prior that really explains the statistical advantage. Why is this algorithm generalizing better, at least in some situations? What are the assumptions about the world that this particular machine learning system is exploiting? So, and I think it's great when we can articulate that. So let me talk about a few of these that I'm interested in that are all related to this notion of conscious processing and system 2 processing. So one I'll talk more about is what I called a couple of years ago the consciousness prior. And it says that the kind of semantic high-level variables that we manipulate with consciously have a joint distribution which is well summarized by a sparse graphical model, a sparse factor graph, where there are many dependencies, but each dependency involves a few variables at a time. Another property of these high-level variables is that they often refer to causality in some sense, right? To agents that can do things in the world that can have an effect, intentions that are about these effects being planned, and the objects that are being controlled, that are, you know, the consequences, that are feeling the consequences. So a lot of language is really about these kinds of things. And so in a way, we're all the time manipulating these causally meaningful entities. Another thing about that I won't talk about much, but that has been talked about in the literature, is that this sparse factor graph, you can think of it just those factors in the graph that connect a bunch of variables together as rules, but of course there are going to be soft rules. This is neural nets after all, but where those rules can be instantiated on many tuples of variables, right? So the same rule can be applied in many places. Of course, we already see that in many ways in machine learning, but this is something to keep in mind. And when I'll talk about attention mechanism, you'll see this notion of objects being manipulated in the neural net as instances that the same pieces of computation can be applied to, and different instances could be manipulated. Another prior that I want to talk about, and also has to do with causality, is the, so I said there's this assumption that the dependencies can be represented by a sparse graph. Now, the thing I mentioned is we care about out-of-distribution generalization, in other words, how the world changes. And how can a learning machine deal with those changes? So here we need assumptions. And the assumption that I'm going to be talking about is that those changes are sparse and potentially happening in only one place if you use the right representation. So under the right representation, the correct high-level representation, the things that change in the world can be localized, can be expressed with language. So anytime we use language to explain a change that happened in the world, so that, you know, a sentence is very short. You can only refer to a couple of things. So this is an amazing property of how the world changes that we ought to take advantage of in machine learning. And then another assumption that people in my field have been looking at, and that I won't talk much about, is that most of the things that are learned in this model of the world that includes causal dependencies are stable despite the changes in distribution. So you know, the whole point of building a good model is that it's going to be robust to those changes. Yes, things might need to change, need to be adapted, but as few as possible, right? So that's connected to the other assumption that the change is localized, that most of the concepts about the world that we manipulate are stable. And these are the ones we want to go after. And then there's another one that I won't talk much about, but is also connected to the consciousness prior. And it says that the kind of temporal dependencies that we care about, that humans are able to deal with, involve very few events. So the causal chains that we can reason over are very short. And that has as a consequence that basically we can deal and essentially get, you know, eliminate the problem of long-term dependencies and vanishing gradients, if the assumption is right. Okay, so now let me dive in some of these things. And I've already used almost half of my time. All right, so why would we care about changes in distribution? So I think this is the reason why evolution might have put these special kinds of processing, system 2 processing in humans and probably in mammals and even birds. To be able to deal with those changes in distribution, agents in complicated worlds where they can't, they're not born with the full knowledge of the world, have to deal with either real non-stationarities because other agents are doing things, or non-stationaries from their point of view because they only perceive a part of the world and then they discover new aspects of it as their life goes on. And I think it's particularly important for agents that have to do with other agents. So if, you know, a lot of people in AI are interested in multi-agent scenarios, and this is, you know, in evolution is an example of that, where there is no fixed distribution, right? The distribution that agents see keeps changing because the other guys are doing things and their policies are changing and so on. So this is a ubiquitous issue for learning agents in the world. And now this problem of out-of-distribution generalization is sort of what we want to address, and then the how we want to address it is something that linguists have been talking about for a long time, and it's called systematicity or systematic generalization. And it's the idea that in order to deal with those new situations in the world, it would be really, really convenient if we build models of the world that have these little parts that we can recombine on the fly in order to explain what we're seeing. So like in the picture here, where we take different concepts that we know and somehow that explains the meaning of this new concept of this special motor thing. So this dynamic recombination of concepts is you know, the question I want to understand better how we could implement, and it helps us deal with changes in distribution that otherwise, you know, might seem impossible because we can, for example, read a science fiction novel that talks about a situation we've never seen that doesn't make any sense because it goes against the laws of physics. But we can read the novel, we can understand it, we can even read the beginning and continue it, and we're doing a good job. So there's been a lot of papers written about how current machine learning somehow fails, or at least gets a performance hit when you do these changes in distribution in ways that are very different from humans that seem to be doing a good job at that. And we've been working, we have a recent paper on this issue in the context of visual question answering. Okay, so I've been talking a little bit about system 2, which seems to be, I think rightfully so, closely associated with the kind of objectives that classical symbolic AI gave itself many decades ago. So what's the connection between this old program and the kind of new program that I'm proposing we should spend more time on? We would like to have the best of both worlds, right? We would like to avoid some of the pitfalls of classical AI rule-based symbol manipulation. We want to build systems that can learn and can do so at a large scale and efficiently. We also want to build systems that are grounded on system 1. Remember I said deep learning is doing good at system 1. But really, those high-level concepts, we can't just manipulate them abstractly, and there are really good reasons for that. They need to be connected to the real world, but also I'll argue that in order to search efficiently in the sort of high level of concepts that I'm talking about, you need system 1 in order to somehow guess good paths, good plans. And this is, if you notice, you're not conscious of how your brain figures out a good path. It just comes to you, right? Or good path or dangerous path, for example. So this is something that's handled by system 1. Another thing is I spent a lot of time a couple of decades ago thinking and demonstrating the importance of distributed representations, which are one of the key ingredients that explain the success of neural nets and deep learning. So we want to keep that. We want to represent objects not as symbols, but as vectors of attributes that are learned. And finally, we want to be able to manipulate uncertainty, and it's something that's not always easy to do with symbol manipulation. But at the same time, we want to bring in some of the advantages of what we find in some of the work with rules and facts and reasoning that makes it natural to obtain this sort of systematic generalization where we combine rules and facts together, for example, in new ways. And with that come an interesting idea which we don't think about in deep learning so much, which is we want to be able to factor knowledge into smaller pieces that can be exchanged for each other so that we can manipulate variables in new ways and instances, and I'll talk about indirection for that. Okay, so the building blocks that I think will allow us to do these kinds of things in deep learning are essentially attention and its variations. And attention is a crucial ingredient of conscious processing. It allows one to focus on a few elements, but there's really a lot more to that. So Jeff already talked about transformers. Transformers are based on these soft attention mechanisms which we introduced for machine translation, where we match a key and a query from two modules, the one on the top, say, and one of the modules in the bottom. And when there's a good match, then some value vector is being sent from the bottom module to the upper module. And actually what it does is it changes neural nets from machines that operate on vectors to machines that operate on sets of vectors. And Jeff already told you about how this could be useful in the capsule setting, but really it's much more general than that. And what's interesting is that with attention mechanisms like this as the way of communication between maybe larger entities like modules in the brain, comes the need for representing names of things in direction. So what attention allows is a dynamic connection between modules. Whereas in a traditional neural net where the connection from neuron A to neuron B is always there, and the weight that connects them doesn't need to be labeled to say, well, this is a signal coming from neuron A, right? So neuron B knows that the information coming here comes from neuron A. But if what neuron B is getting may come from A or C or D, then it becomes really useful for that communication to include not just the values, but also what corresponds to keys in attention mechanisms, which essentially is like a type or a name, which allow to refer indirectly to the content wherever it comes from. So that allows us to keep track of these entities, which are no more like the capsules. So they're not single numbers, but they're more like an object that can be sent around and manipulated. Okay. So I want to say a few words about the connection to neuroscience and cognitive neuroscience. It used to be, say, in the previous century, that working on consciousness was kind of taboo in many sciences for all kinds of reasons I won't have time to talk about. But fortunately, this has changed. And in particular, in cognitive neuroscience, there's a lot of work in this century and a little bit at the end of the previous century. In particular, the global workspace theory by Bars, and then the more recent work in this century by Stan Dehaene, which really established these theories to explain a lot of objective neuroscience observations. And it's interesting, I think, for machine learning now to come and bring in something different, to bring in, why would this be meaningful? Why is it that the brain would have this kind of bottleneck where information has to go through this bottleneck, just a few elements, to be broadcast to the rest of the brain? Why would we have a short-term memory that only contains like 6 or 7 elements? It doesn't make sense. I mean, your calculator can do better than that. So there's going to be a reason for this. And I think machine learning can help us uncover those reasons. So I'm going to skip that. But the bottom line is get the magic out of consciousness. There are connections to language, but I'm going to skip that. So the consciousness prior I already mentioned, but let me try to convince you. So we're talking about assumptions about the world. And there's an extraordinary property of the kinds of concepts we manipulate with language. And that property is that in a single sentence, we can say something that's true with very high probability, even though that sentence contains very few variables. If you think about it, like if I'm trying to predict 1 pixel given 4 other pixels, I'm not going to be able to have a very strong prediction in general. Whereas I can say things like, if I drop the ball, it will fall on the ground. And this is like almost certain. So what this is saying is that at that level of representation, our knowledge is represented in this very sparse graph where each of the dependencies, these factors, involve 2, 3, 4, 5 entities, and that's it, right? Of course, these are connected to each other in a complicated way, but reasoning is about traversing this graph in order to be able to infer things that we care about. All right, so that's the sparsity assumption. And there's the other one I mentioned, which is that not only the graph is sparse, but that when it changes in a sparse way. And yeah, let me skip meta-learning because time is flying. So why does it change in a sparse way? So intuitively, the reason it changes in a sparse way is because of physics, right? So agents are at a particular time, at a particular place, and they do something, and they have an effect. And eventually that effect could, have consequences all over the universe, but it takes time. And so if we can build models of the world where we have the right abstractions, where we can pin down those changes to just one or a few variables, then we will be able to adapt to those changes because we don't need as much data, as much observation, in order to figure out what has changed, right? So that's related to a beautiful theory and concept that I took from Bernard Shopkoff and collaborators called independent mechanisms. And here it's illustrated graphically, and I have a little example with the kid and and the glasses. So, if I see you right now and I put on some dark glasses, what happens is that only one bit changed, right? The bit in the right abstract space that flips and says, I have put on some dark glasses. If I had to explain this at the level of pixels, I would need to change so many things, like the way I do vision and everything. Whereas if I have just the right representations, I can explain that change much more easily. So, and so one consequence of that is that when you have the right model, in particular the right causal model, when there's a change in distribution, you can adapt to that change very quickly. So this is a claim and a hypothesis, and we've been doing a lot of work to validate it. In particular, we've used this to show empirically, and then more recently with theory, that the right model, the model that predicts the right causal structure, at least in this very simple case with just two variables A and B, can adapt to a change in distribution due to an intervention, and especially an intervention on the cause, much faster, in other words, requiring less examples, and so faster as in a statistical sense, than the wrong models. And so you can use that in order to figure out what is the right model, right? So you could, if you only had two models, you can like run them in parallel and see which one is converging faster. But we have generalized this in another paper where we learn whole graphs, whole causal graphs. So we just have an experiment where we know the ground truth graph, we do a change in the graph by an intervention on one of the nodes, and the learner just sees the data before and the data after, and it tries to learn the model. It doesn't know the model, right? But it also learns to predict where the intervention has taken place, and after seeing many of these changes in distribution, it actually figures out the right causal graph, which is not obvious. If you only see the observations and no changes in distribution, it's actually not possible to correctly recover the graph. All right. And then the last bit of recent work I want to talk about has to do with another consequence of the consciousness prior, and that has to do more with the architecture of these neural nets. So I mentioned at the beginning that we would like to be able to recombine pieces together dynamically, and I mentioned how attention mechanisms were important for this. So attention mechanisms are very interesting because, well, on the one hand, they allow us to focus on just a few things at a time that are going to go into our short-term, conscious short-term memory that we are manipulating and seeking sort of coherent interpretations for. And attention mechanisms can also be used to decide which module is talking to which module on the fly. So this is what we've been exploring with this architecture, which we call recurrent independent mechanisms, or RIMs, where this is just a recurrent net that can be, a drop-in replacement for LSTMs or whatever you like, and it has a modular structure. So instead of having one homogeneous state, it's broken into a bunch of modules. Each module has their own state, and the thing is, inside each module is like a normal recurrent net, whatever you like, but the way that they communicate with each other is through a bottleneck, is through a attention mechanism that, first of all, decide which of the modules are going to be activated, which of the modules are going to be allowed to speak, and then also we use attention mechanism to exchange information between the modules in the form of these key value pairs, in terms of something like the capsules, basically. But we think of them as objects that are going to be matched. So if you think of functions in programming, right, you have typed functions. Functions are nice modular pieces that can be composed with each other. And what they have are these typed arguments. In other words, a function expects like the first argument to be of some type. And you can think of the query that a particular module expects for one of its arguments in the same way. So each module essentially is saying, oh, well, for my first argument of the work I'm doing, I'm expecting some object of a particular type. And type is going to be represented by a vector, a query vector. And if that query vector matches well with the key vector of an actual object that's produced by another module, then these two guys will be sort of connected together, and the value produced by the source module will be sent to the module network. Now, all of this, of course, is not done the way that I'm saying it with discrete choices. It's all done in a soft way with soft attention, and so you can backdrop to the whole thing. And it works really well. So this is reinforcement learning experiments on Atari. But what's most interesting, where is it? No, I have other slides. What's most interesting is that this worked really well out of distribution compared to other LSTMs. So if there are changes in distribution, if you extend the data to longer sequences and things like that, this works amazingly well. And we have ongoing work extending this in various ways that I won't have time to talk about. So let me conclude. I've told you about a bunch of hypotheses about the world which I'm exploring with my collaborators or have been discussed in the literature that I think can be incorporated in machine learning systems to implement some of the computational abilities that is associated with System 2. And with that, I thank you for your attention.
So finally, we move on to the panel, and we're extremely fortunate to have an exceptional moderator in Leslie Pack-Kelbling, who is a professor of computer science and engineering at MIT. I won't go over her many honors, but she's an extremely highly regarded roboticist, as well as the founding editor of the Journal of Machine Learning Research.
Okay, thank you. So we have all kinds of really interesting food for thought from the speakers and also from the stream of questions, which I've been keeping my eyes on. I will try to perform some clustering and filtering on those questions, because you wouldn't want them in their raw form. And so there's two categories, I think. One is there's a set of questions that are technical, and there's a set of questions that are kind of meta about research and ideas. So I think we'll start with some technical questions and then go to some of the meta ones. So one technical question is the connection that you feel between neural networks as a computer science concept or as a machine learning concept and neural networks as an analog for what goes on in natural or human computation. So I guess for each of you, how important is it to you to stay true to what we know about natural computation?
Okay, I'll start.
You can have that.
I see natural computation, as something that can inspire us in coming up with engineering models. So we can learn all sorts of things about how people do things, and they will suggest how we might try and do things. So for example, I think taking a system with millions of parameters and training it from scratch and hoping that it would do anything sensible, you wouldn't have believed that unless you knew the brain did something like that. But the details...
Jeff, we don't hear well.
You don't hear me well?
You need to hold the mic.
Okay. Do you hear me well now?
Very well.
Okay, so I think the brain inspires us, suggests things. In particular, it suggested that progressively adapting weights using lots of data would allow systems to perform complicated computations without any programming. And that idea is fairly bizarre. I mean, you wouldn't have believed it unless there'd been an example of things that did that.
Good. Other guys?
Yeah. I mean, clearly it's an inspiration. So things like convolutional nets are obviously inspired by classic work in neuroscience. A lot of ideas that we use now have their equivalent in computational neuroscience. Things like, divisive normalization, which is kind of a standard tool now used in neural nets, rectification, things like this. And there's a bunch of other things that we discover. People, a few years ago in various places came up with the idea that a neural net could be augmented by some associative memory. And then, you look at the brain and say, well, that looks like a hippocampus kind of thing. It's not really precise, but clearly there is, some parallel. I mean, there's like the almost cliche analogy between, AI in aviation, where we get inspiration from birds, but we build things that don't flap wings and don't have feathers. So it's a bit of the same thing. But ultimately, I think many of us got into this field because we wanted to understand human intelligence.
So let me add something. I agree with all of these things, obviously. So my drive has been that there's what I would call an amazing hypothesis that a few simple principles could explain a lot of what is going on in the brain. Of course, the brain is also a bag of tricks, but there are a few simple principles that allow us to do these very complicated general tasks. And if we do research in machine learning and AI, we can test some of these principles, and that can give ideas to our friends on the brain side of things. And so, in a way, we can have a jointly beneficial exploration where we uncover these simple principles that both help build intelligent machines and understand how the brain works and what is intelligence.
Cool. Okay, so another thing is that I noticed, and several people in the audience noticed, I think that you each alluded to some aspects of representation and reasoning that I guess some classical AI people would embrace and call part of their toolkit. Things like compositionality, standing for, learning latent representations, sparsity, factoring, and so on. And yet sometimes some of you speak a little disparagingly, I think, of possibly the symbolic AI world. So can we be friends or can we not? Jeff?
Well, we've got a long history, like. So the last time I submitted a paper to AAAi, it got the worst review I ever got. And it was mean. It said, Hinton has been working on this idea for 7 years and nobody's interested. Time to move on. Now, the idea was the idea that you might represent the meaning of a word with a vector. And it takes a while to sort of overcome that. And we should be sort of, right now, we're in a position where we should just say, let's forget the past. And let's see if we can take the idea of doing gradient descent in a great big system of parameters, and let's see if we can take that idea, because that's really all we've discovered so far. That really works. The fact that that works is amazing. And let's see if we can learn to do reasoning like that.
But I'm gonna get answers from those guys. But let me suggest that just because AAAi was mean to you once, or maybe several times, that's not a way to go, right? We shouldn't do induction on that and just be mean all the time.
I completely agree with you. I'm just trying to explain why there has been some
I get that.
slight animosity.
So my answer is very similar. In fact, I had it in my conclusion slide, replace symbols by vectors and logic by continuous functions. And the reason for this is because we want to make reasoning compatible with learning. And the only learning that we know works is gradient-based learning, so we have to make it compatible with gradient-based learning. So we have to make things differentiable. And I don't know how to do this precisely. I know that the very idea of this is a anathema or shock or whatever to people who are really interested in logic, because you're going to have to abandon a lot of the body of work that sort of came out. And a similar phenomenon occurred a few years ago with sort of transformers and other similar models in NLP, where a lot of linguistic knowledge is basically not very useful anymore for those.
It's all been said. As you also heard from my talk, I think we should look forward and think about the best ways to get, at the same time, the advantages of deep learning and solve some of the problems, like reasoning and I think language understanding and so on, which are associated with classically with symbols, but I think can be also addressed using more modern approaches. And I think attention mechanisms in particular are a key to this, as I was trying to convince people of.
So do you really think that there are no useful alternatives to gradient-based learning?
Well, okay. So all the learning methods that people have ever come up with that have worked are based on optimization of some kind, right?
Random forests?
Huh?
Random forests?
It's some sort of optimization. So, I mean, it's greedy, but
Okay.
yes, okay. And there is, marginalization with Bayesian and stuff like that. I mean, you can qualify this, but to some extent, that's the case. If there are other methods than that, I'd be interested in knowing what it is. That actually raises the question, does the brain minimize an objective function? Not clear. Okay, second thing, if you're going to optimize a function, what are you going to optimize it with? Either it's zeroth order, gradient-free, or first order with gradient, or higher order, which still use gradient, but use other things. Zeroth order is way less efficient than first order, so if you can use a gradient, please do it. In fact, there are methods in reinforcement learning for which the objective is not differentiable, that use a critic whose purpose is to make the objective function differentiable by approximating it by a differentiable function. So, yeah, gradient descent works.
That's good. That wasn't actually the question, but yes. Okay. So maybe we should go to some of the questions that are a little bit more about methodology and such things. So one thing that I think so there are a lot of students in the audience, and so there are a lot of kind of student-related questions that have come up. One concern I think that a lot of students have is that it seems like that there's a lot of research right now that's going on in big companies that have enormous resources. And the question is, well, what is the role of universities when Facebook and Google and so on can mount these enormous projects that it feels like a student can't compete with?
Can I take that one? So I still think that the really original ideas come from a graduate student in a really good department getting good advice so he doesn't repeat history, or she doesn't repeat history, but spending several years thinking about how to do something. And that can be done in a big company, but I think the place where it's done most is in universities. I think that's what universities are really good at.
So I can add something to this.
Yes, please do.
There are a lot of really hard problems in AI which can be studied under the microscope of toy problems. I mean, I think we have turned our back on toy problems too quickly in this field, and in machine learning especially, focusing on like these really hard benchmarks that take 2 weeks to run with 2,000 GPUs. But there are really interesting problems where you can analyze a question, you can do experiments with reasonable resources. Now, I admit that sometimes it's frustrating not to have those resources, but there are also environmental issues related to using that much energy.
Well, so I propose that we create a new conference, the International Conference on Deep Learning on Toy Problems.
Can you repeat that? I actually didn't hear you. Deep learning?
On toy problems.
On toy problems, I see. Okay. Okay.
Actually, this relates to my suggestion to Jan some years ago. I wanted to have a conference called MNIPS, where your algorithm had to be tested on MNIST.
Very good. So I guess to continue some of this student thing, I mean, one thing that I think students are also interested in is what should they be reading and studying? And I noticed that actually you all mentioned concepts from the previous era of, say, probabilistic modeling. So, but what do you think students should read?
It's better if they don't all read the same thing, that's for sure.
I think that's actually a really important point, right? We shouldn't be a monoculture.
I had an advisor, and his advice was reading rots the mind.
Warps.
No, rots.
Rots. Oh, okay.
So his advice was, don't read the literature, figure out how you'd solve the problem yourself. Once you've figured out how to solve it, then go and read the literature.
Yeah, I'm for that. You guys have anything to add?
I think Feynman had a similar recommendation.
Okay, let's see. Yeah, we don't want most of these questions. Okay, let me come back. So here's another kind of question I have lurking here, which is, so one of the start of this session was good. We started with convolution, and then that's not so good. Maybe we need capsules, and transformers are useful. And there's this sense that we are collectively as a field coming up with mechanisms that help, right? Different kinds of structural biases and so on. Do you think there's going to be 6 of those, or like, are we going to have to find 60? Or is there a sense in which there's a closed set of these kinds of mechanisms that will get us to, say, human-level AI?
The smaller number, the better, but we don't know.
Yeah, I'd say it would be nice if it were a small number, like, say, 6, 10 classes of architectures. Whether that's possible or not is not entirely clear. I mean, what gives us hope, perhaps, is the sort of apparent uniformity of the cortex. But then there is only a small proportion of our neurons in the cortex, so all the rest doesn't seem to be as kind of isotropic or uniform.
Do you have reservations about the research activities that some of the big AI companies are doing?
Yes. For example, if it's gonna help the fossil fuel industry.
No, actually, both Facebook and Google data centers are becoming carbon neutral, and will be by the end of this year, at least for Facebook. I'm not sure about Google, but.
I think they ought to be doing things about fake news, but...
Yeah, in fact, we are.
I should say that's just a personal opinion.
And I would add, be nice if these companies with a lot of AI expertise were not also trying to make money by building things or doing research for military applications.
I think that's something all 3 of us are agreed on, and I was actually quite impressed that Google cancelled a project that would have led to huge billions of numbers from the Defense Department because Googlers were against it. That made me feel that Google wasn't such a bad company after all.
Yep, Facebook doesn't do this kind of stuff, so it's never been a question.
Okay, so let's go to something mildly less controversial. So where do your old and new ideas, where do your ideas come from? How do you decide which ones to work on?
It comes in the morning when I wake up.
Okay, how do you decide which ones? All of them?
No, it's system 1. No, seriously, I mean, it's intuition, right? And then, of course, you do experiments, and it fails, and it fails. Well, sometimes it works. And you have to listen to that intuition, and that's how we do science, right?
Anybody else?
Well, I mean, certainly, I'm very reliant also on intuition and things like this, but I think you have to identify the crux of the real problems, the important problems, and then ideas come and they become obvious after the fact. At least they're obvious to you. It might take 20 years for the rest of the world to realize they're obvious, but it's happened. But it's kind of that kind of progression. So I had that feeling about multi-layer neural net, way back in the 80s, that this was kind of an obvious way forward, and then convolutional net, which was an obvious way forward. It took a long time for this to become prevalent, and now I have this feeling about self-supervised learning, about the problem of dealing with uncertainty and in prediction. Those are problems that we need, like important problems that we need to solve, rather than sort of, kind of, it's always useful to, of course, improve the, by various methods, improve the performance of practical systems, but I'm more interested in things that have a long-term impact.
So there's a recurrent kind of theme in the questions about the fact that neural networks were somewhat unpopular for a while, and some brave people continued to work on them, and whether...
Stubborn.
Excuse me? Stubborn. So stubborn is good. And so the question is how, I mean, if you're, imagine that I'm a researcher currently attached to an idea that's wildly unpopular at the moment. How should I proceed? What should I do when people write mean reviews and nobody likes my research?
So I guess the first thing you should remember is that most ideas that are wildly unpopular because they're no good. So that's the tricky discrimination, right?
Yes.
And I don't know.
Okay. No, if it's not neural networks, give up. Is that what you're saying?
No, I think you have to look at evidence, right? It can't be just your intuition. There's a fine line between taking into account the evidence and just going by faith. But you do need that faith to move forward, and maybe it failed the first time, but there's a small twist that will make it work.
I think if you really believe in an idea, you should never give up on it.
I'm for that.
That's why I'm still thinking about how to make Boltzmann machines work. And I have a piece of logic that satisfies me at least. If you have logic, yes, logic. And the logic goes like this. If you believe in an idea and you have good intuitions, you should work on it. And if you have bad intuitions, it doesn't really matter what you do.
Okay, good. One thing, actually, this is a question of mine, really. So Jeff said that it was important for graduate students to think for a long time about a difficult problem. And I wonder whether you feel, I feel like the current publications cycle is fast and short-sighted, and I'm nervous about its effect on the field. And I wonder if you guys feel the same way.
I'm discouraged. The current generation of researchers in computer science and machine learning and AI seems to be very focused on short-term gains, just working on the next conference deadline. And so, I have students coming to my office and say, what can I do the next 4 weeks? Because there's this deadline.
None of you do that, right?
And I think it's really bad for the field. That we need to change something structural that will encourage people to take more risks and work on a longer-term horizon.
What can we do?
I think, there's a whole spectrum, right? I mean, there is certainly a lot of usefulness in sort of, getting the records on the benchmarks and everything. This is very useful in the end, so nothing wrong with that. The problem is, and as our field grows, it becomes more and more applied because there's more and more people who are interested in those applications. That's why they came to the field. So the question is, what is the total absolute number of people working on kind of more longer term, and whether they still have a voice in conferences and venues that tend to be more application oriented, like vision conferences, for example, or natural language processing conferences. So there should be a space for conferences that are more on methods, and where there is no emphasis on beating records. Perhaps this newly proposed conference on deep learning for toy problems. But that may allow people to still have a high rate of publication, which is required by our system of getting jobs and stuff like that, but still while working on kind of long-term complex questions, ambitious questions.
the publication pressure is much stronger than what it was when I was a grad student. And the number of papers that students are producing in the term of their PhD is just crazy, right?
We would not admit ourselves in our own PhD program.
Absolutely not. The question is whether the integral of the content of the papers is different.
Yes.
Right? It may or may not be.
And actually, one side effect is once a paper is being published, like a half-baked thing that goes into a conference paper, once it's been accepted, they move on to something else very often. And yeah.
Yeah, I have a model of this process of people working on an idea for a short length of time and making a little bit of progress and then publishing a paper. It's like someone taking one of those books of hard Sudoku puzzles and going through the book and filling in a few of the easy ones on each Sudoku. And that really messes it up for everybody else.
Very nice. It's 7:30. Do you want us to stop? Okay, a couple questions from the audience. I don't know the mechanism. Oh, there's a microphone there and a microphone there. Okay. Microphone. Okay.
Can we call doing AI doing science? Yes or no? And
So the question was, can we call doing AI doing science? And the answer you have to give is yes or no, and the answer is yes.
Well, I think there are different things you can do in AI, and some of those are more, on the side of engineering, and some are more on the side of understanding something, and then that's more on the science side.
Yeah, it's engineering science, right? So there is the creative part where you conceive an artifact, and then there's the science part where you analyze how it works and why it doesn't work and things like this. And it's very often the case in the history of science and technology that the creation of the artifact preceded the theory that explained it. A good example is the invention of the steam engine. And it took 100 years for people to figure out thermodynamics and explain the limitations of thermal engines and things like this. So we are at the stage where we can build steam engines. And the question is, where is thermodynamics? What is the equivalent of thermodynamics for intelligence? I mean, that's kind of my big scientific question.
There, at the microphone.
Thank you. Excellent talks. I have two questions. One is, I don't know if there's so many papers these days, but if any of the three of you had looked at this paper from Cholette from Google, where he's talking about not necessarily what general intelligence is, but more about ways of what it's not and ways to potentially measure it. And the second question is, human beings have been able to be generally intelligent and create things like mathematics, so we can create a formula analytically like F equals MA or equals MC squared, and the amount of computation is almost as simple as 2 times 3 equals 6. So it only takes a few transistors, maybe a few watts or milliwatts, whereas a lot of the deep learning stuff is incredibly powerful in general, but it takes megawatts or kilowatts or hundreds of watts. And so is there some possibility that with these neural architectures that we don't necessarily ultimately need to have things that are so computationally complex or with so much capacity?
Well, F equals MA came out of the brain of a person with a huge number of neurons, a huge amount of computation. And if we want to have machines that can come up with these kinds of things, even though the end product might be a simple equation, there's a lot of computation and experience and learning that was behind that.
Well, I'm not arguing that.
No.
Sorry. Yep, totally
We're gonna. I think I'm told that we only have time for one more question, which I'm sad about.
Here,
so,
yes.
We're gonna take that question right there, at the mic in the middle.
Yes, one for each mic.
It seems like you're in violent agreement on so many things. The nature of priors that might be required, the value of self-supervised or unsupervised learning. I'm wondering if amongst you on some of the finer points of these, you feel there might be disagreements or differences in how you think the approaches should be taken or what elements are important.
Well, Leslie already tried that on us and it didn't work.
Oh, I can tell you one disagreement between us. Joshua's email address ends in Quebec, and I think there should be a country code after that, and he doesn't.
And I'm staying out of that debate.
Okay.
One question.
I think
Last
on
one.
that note,
Last one.
we are done, says Vince. Okay, so thanks very much to our speakers.